Hello, my name is Brian Hardeman from Thunderhead Engineering, and I'm going to speak to you today about some recent research and development efforts here at our company. I'm going to start off talking about movement research that we've been doing for the last couple of years. This is primarily related to Pathfinder and the simulation engine in there. One interesting research project that we've worked on just this year as a result of the global pandemic is working on adding social distance type behaviors to the Pathfinder simulation engine. This was requested by customers, obviously, and was a clear need inside the simulation for event managers and property managers looking to reopen venues this year in light of the pandemic. And so challenges there are primarily with trying to design the simulator, which, Pathfinder being initially an evacuation simulator, add in a new behavior that would help maintain a social distance specified by the user, typically 2 meters or 6 feet. For the US folks. And while this is also very important as providing visual information for clients in that, I think often actually these venues and events will be run with more procedural, they'll put marks on the floor that tell you where to stand. But often you need to present, what it's going to look like when you run these kind of simulations. So embedding in the simulator some capability for the agents to maintain a separation distance was important for us this year. Initially, we were able to do this with a comfort distance, which was an existing parameter inside Pathfinder that provides, that has been existing in previous versions. But this was defined as the sort of the waiting space, the personal space, where when occupants are idle, they typically don't want to move closer than that to one another. This had some limitations, though. I mean, if you're setting that to a large value, it's really not quite what that property originally intended. It would work, but often agents would bounce around a little bit or wait very close to walls or boundaries. And the biggest problem with that approach, that workaround, was that it didn't support groupings of occupants. It applied equally everywhere, whereas really in real-world scenarios, you needed to model those social cohorts that may be willing or able to stand close to one another but want to maintain distance from other groups. So here's a brief video of using comfort distance in a Pathfinder model just to show kind of how it would work. And you can see up here in the upper right-hand model that you'll see some of these, mostly the agents are staying their distance apart, but you see quite a bit of wiggling, particularly as people sort of jostle to get through the door. And that was one thing that we were trying to avoid in researching a new way to do this. So the new approach is kind of a multi-step approach. The first step is to identify the occupants in the model that are going to be identified for socially distancing. So we're ignoring members of your own group. Ignoring, somebody that you're giving assistance to. So that's just sort of a first pass filtering. And then we adjust some of the other behaviors that take place within Pathfinder. We reduce the seek separation behavior, turn off passing behaviors, and reduce the penalties for moving backwards. Then the real key to this is for every agent at every step, we generate a social distance cost that's part of the inverse steering calculation and the weighted direction estimates. So a comfort distance is calculated based on calculating the projected distance of every other occupant that you're trying to distance from and dividing that projected distance by the desired comfort distance or desired social distance. This uses the projected locations in time based on everybody's velocities and also includes the agent's reaction times. Then this gets normalized in a range from 0 to 1, and then the maximum cost is assigned to the lowest comfort level. So the area where you're farthest, you're much closer than you want to be. So that one gets the highest cost. And essentially, this becomes a strong function since some of the other steering behavior components have been lessened in this case, and essentially pushes occupants away from one another, driving them toward that ideal distance. So it kind of acts as a dynamic relaxation step as it is iterated, from step to step. And there's a bit of a bias to the front, and I'll explain that a bit more in a moment. But we can see here, now this is an example with groups in this case. So occupants of the same color here are shown, are members of a group. So in this case, they're it's okay to remain now the old comfort distance from a member of your group, but you're going to maintain social distance from those outside of your group. And on the left, there's no grouping being enforced, or the social distance is the same for everyone. And on the right, you're being allowed to stay closer to your group members. And you'll see that this method now supports that and works reasonably well and is a little bit more stable than the comfort distance approach. Now, there were a few challenges in the midst of developing this new steering behavior to take into account social distancing. One of the first ones we ran into was group compression, and it was kind of an odd mix of the behaviors working together, that as groups are, if you have a large number of people waiting and collecting in an area, as the groups form and push through one another, there was sort of an incremental reduction of the distance in the crowd, which would then sort of lock them in and trap them so that they couldn't back up. The fix for that was to reduce the social distance desire in the back versus the front, and this would allow them to back up some to maintain distance. So you're more aware, essentially, of social distance in front than in behind. Side effect of this, that in an overcrowded room that's initially overcrowded, which may not be a really common occurrence, but we see this in sample problems, that there'll be kind of a tendency to hug toward the back of the room, so the people in the front will maintain a greater distance and a lower density than those toward the back. But here's an example of showing the problem before we corrected it. And you'll notice it sort of starts out looking okay, but as more and more people enter the space and the groups sort of jostle, the social distance between everybody gets smaller and smaller incrementally, and they're being packed in. So it's sort of a one-way ratcheting down of the average distance. So here it is. Again, on the left is the before, and now on the right will be the after. So these are running in sync, and you'll see with the fix on the right, you'll see occasionally people sort of are inching backward a little bit to try to maintain that distance better. But overall, you see there's a much closer maintenance of the average social distance in the updated case. Moving on to another challenge we saw in this was bouncing, and this was also evident in the earlier, using the comfort distance to model social distance behavior. But it would tend to manifest itself as an oscillation, particularly in queues, and it's caused as somebody's trying to get through the door and everybody else has to back up to make room for them to go through, and that would kind of send waves through the model and create these oscillations. And you can kind of see this again, particularly in the upper left, but in all of these, you can see people are sort of getting, oops, I need to get out of the way and let someone through. And that would sort of send these waves back through the model. So here it is after correcting for that behavior. And you'll see that it's much more stable now. And in this case, this is showing a few different comfort distance and initial occupant densities. And the yellow circle is depicting the entire comfort distance. So ideally, you have no one else significantly inside that circle. As part of this work, we also added a bunch of social distance quantitative outputs to Pathfinder to help quantify different scenarios that you may be modeling in a venue, and different approaches to getting a crowd through a particular space. So there's quite a bit of data dumped into a couple of CSV files. One that's called the transient file, which contains information about the closest occupants at each reporting time and how far apart they are, and then the number of occupants that are within 1, 2, or 3 meters at any given time. So that can kind of be used as a gauge of how well social distance is being maintained. And then there's an accumulated file that then sort of shows which occupants spent the most time near one another, and how long, the maximum number of people you would have had for 1 minute or 5 minutes within particular distances. And this can be used as sort of almost like an exposure tracking. Moving on, another really interesting problem that has been worked on this year, this one's been really headed up by one of our really sharp interns, is implementing proper queuing into Pathfinder. The way Pathfinder worked in the past is that queues were more implicit than implicit. It was basically, occupants would wait to move through a door or any other waypoint that was in their behavior specification. But there was no ordered queues or orderly explicit queuing behavior inside Pathfinder. So we've embarked on a research project to work on how we would implement that. And so in Pathfinder, we're defining a queue as a structure that is explicit and allows occupants to join into that line and move through to complete a behavior. The hope is that these will be simple, but able to be chained together to create more complex structures. So, the simplest is moving through a line and getting to the front of the line, maybe at the counter. More complicated one would be something like at the security line at the airport, where there's multiple lines. There's a line for people that have been pre-screened. There's lines for those that, can jump the line because they're have extra security screening. And so that would require a combination of multiple queues to accomplish. So the way this is envisioned for Pathfinder is that a queue is made up of two primary components. There's the path, which is essentially the line that you're going to take as you queue up, which in reality might be marked on the floor or by marked with ballards and tapes. And then a service that you're intended to do at the beginning of that queue. Now that service is represented as a location, and it could be as simple, it could just be going to a point before moving through a door, or it could be something like a security gate or something that might have a time or a delay. So the idea here is that a queue structure within Pathfinder will always require a service, but there may or may not be a path leading to the service. So this base structure is that union of a service and a path. And the idea is that you'll be able to add these queue definitions into behaviors in Pathfinder. So you'll be able to say, for instance, perhaps this occupant group will come into a model, move to a certain location or go to a lobby, and then needs to enter a security queue or a ticket queue. And then those will be explicitly added to the behaviors of those occupants. And then the occupant will attempt to go to that surface until they have completed it, and then they will move on to the next step in their behavior. So if the service is presently busy, then they will go to the path and form a line, as well if a line has been defined. So some examples of these, you could have just a simple service, you could have a collection of two services or more. You could have a single line leading to a single service, a single line leading to multiple services, or vice versa, a single service with multiple lines. The idea is to have maximum flexibility to represent real-world structures that you see in managing events and crowds. So one simple example would be a door queue. This one would be defined as a location that's just in front of the door, and then no particular and just a single path leading to it. So in this case, there's a small example Pathfinder model here, and this is based on internal test models that we've developed at the moment. We're hoping to release this, probably some preview queue capability within the next 1 or 2 point releases, and hopefully have a more complete queuing system available sometime next year. But the door service here is just that point before the door with a 1 second wait in this particular model. But the concept is that you'll be able to assign random wait times, a distribution of wait times, or all sorts of flexibility to manage, what's going on at that service location. Like perhaps, it's a security card reader, and every 5th read or random reads between 3 and 5, it has to reread. You could model that with the system we have in mind. And so here you can see somebody goes up to the door, they wait for a second, they'll move on through, and the next person, clone in this case, moves right on through. The next example is more like a ticket counter at, say, a museum or a sporting event or something. Where you might have a single counter with a few agents processing payments and issuing tickets, and a single line that has been marked out and taped out in the venue and that people need to follow. So in this case, you have that it's a service, but with 4 service locations, and then a single path leading to those. So once you come to the front of the line, you wait for the next open service, move on. And in this case, each of those service locations could have different wait times or distributions of service times. So we'll take a look at this one. This one's sped up from real time a little bit, but you see people are joining the next available service and then moving on to the next part of their behavior, which is to leave this particular room. And then finally, we have an example where we're chaining some of these queues together. This is a very simple one, but the concept hopefully will be built upon for more complicated models. And this one shows that they're going to first enter one queue, then enter a second queue, and then go to an exit. So in this case, the first queue is at the desk and the second queue is at a door. It moves a little bit fast here, but you can see them snake through. They all visit the desk, and then they all visit the door, and then they all move on. And as I said, we hope to have that queue information available and previewed within the next couple of releases. Up next, we have some research work that was done this year by our co-founder, Dr. Swenson, on crossflow and counterflow data gathering. We've had a desire for a long time to improve the crossflow and counterflow behaviors within Pathfinder, but it's very difficult to find the right behavior models and the right data to validate against. But Dr. Swenson has been using lately a lot of data that's been put out at the Research Institute at Jülich in Germany. In particular, there's a thesis by Stefan Holl, and there's a database of tests that were done. And these are very useful tests, in our opinion, in that they're going to allow us to replicate and model different human behaviors and verify them against some very carefully controlled experiments. Now, these are controlled in a good way in that the flow rates and the conditions were controlled, but the users are acting very naturally. It's not quite like I don't know if you've ever seen the evacuations from an airplane, where they have to happen in 90 seconds. It's almost like they have trained people in there to do that, because, and if you've ever been in an airplane, it's hard to imagine all of those people ever getting out in 90 seconds. But anyway, this data, I think, will be very, very valuable. And there's a lot of, I encourage people, if you haven't heard of this data set at this Pedestrian Data Archive at Jülich's website, I encourage you to go check it out. Now, the first thing we did to be able to try to use this in our research and development was to process the data, and they give you data that they have identified from the video footage for each occupant and with their position and time for each frame of the video. So we took this data and processed it so that we could actually load it into our Pathfinder results viewer as if it was Pathfinder results. This gave us a lot of capability to be able to visualize the data and see what's going on and interpret it, as well as then use all of our data analysis tools for creating density plots and other post-processing. So here on the right, you see an image of this experimental data that's being displayed in Pathfinder for analysis. And this is one of the Crossflow experiments where people are coming in from the right and moving to the left, and coming in from the bottom and moving to the top. So in this particular experiment, it was 1.2 meter width, and there was flow. And this is just showing, again, this is using the post-processing available and processing these files, in that this one reached a steady state. And so it's from, say, 20 seconds to 2 or 3 minutes into the model, that there was a steady condition at this intersection, and it's a good data point to look at for evaluating crossflow movements without jamming. So here's an example of that playing back in the Pathfinder results viewer. Again, this is just demonstrating the steady flow of this particular case. So I think this particular video skips ahead a couple times. And we learned a lot from this, just trying to qualitatively even look at how people are navigating the intersection and how people are moving past one another in this space. One thing that we found, and then we tried to recreate this. Our first step was, our hope was that we could tweak some of the existing properties in the Pathfinder movement model and improve our crossflow behavior closer to what we see in the experiments. Unfortunately, we were not successful at that, but we did learn a lot along the way. So on the left here, we have the standard Pathfinder applied to this particular problem. And what we'll see there is that Pathfinder has trouble with jamming in this case, because essentially when our agents avoid one another, they're doing it in a fairly uniform way, but when it happens in the presence of a crossflow, it's being biased and pushed downstream, and both of those incoming flows sort of get pushed downstream, and so you end up with contention and jamming at the downstream corner. And when we look at on the right, we tried to improve it, and it did get slightly better by changing some of our parameters, but it still didn't get us where we needed to be. Although you see it's not jamming in the same way that the original method did. Although you still see some of the red, people are being pushed pretty far downstream, as well as some of the blue are being pushed quite a ways downstream. And what happens in the original parameters is that this will actually degrade into the point where it's completely locked up and won't continue anymore. But what we saw in observations, now again, this is back to the experimental data, is that for the most part, as occupants navigate this intersection, they do not move significantly left or right, which is a good target for us to try to match in Pathfinder. So if you look at these traces on the floor, you'll notice that, I mean, they add some wiggle, but there's not a definite bias upstream, downstream, et cetera. They basically manage to maintain a similar path. And this happens because essentially people have to slow down and they wait for an opening and then they move into the opening, which I think sounds very natural. It's much the way, we move as pedestrians or even in traffic. You slow down, you wait for your spot, and then you push through. But I think this also means that there's an upstream awareness. You have to look upstream for that gap that you're going to go through after you've slowed down. So we haven't not yet incorporated this into Pathfinder, but we've learned a lot from this. So in summary of the crossflow research that we've done this year, we've processed the trajectory data and we've been able to display it and recover other information that was presented in the thesis, such as the speed density curves, fundamental diagrams. We've experimentally measured the speed density and determined that the speed density is not a sensitive indicator of when we'll have jamming behavior in crossflow. I mean, some of the experimental movements did progress to where they could not maintain steady state, right? So where you would end up with queuing and jamming. But it doesn't seem that there's a clear correlation on simply things like fundamental density. And as I mentioned in the last slide, occupants seem to resist being pushed, and it's more of a slow and anticipate openings. And the current implementation inside Pathfinder allows people to be pushed downstream more than they should, which leads to the jamming behavior. So a challenge for us will be to try to replicate that movement and bias the decision-making upstream. But we're excited about this data set and its opportunity to help us improve Pathfinder movement, not only for crossflow, but also for counterflow and other intersection movements. Up next, we have a discussion of some movement speed and smoke. This is a minor way that we've added to combine PyroSim and Pathfinder data. So we've used the movement speed in reduced visibility correlation published by Friedolf, and previously, the way you could sort of trick Pathfinder into slowing people down is you'd say, okay, at time t, I know that this particular room in my model is going to have reduced visibility, so you could set a movement modifier to slow everyone down in that room at a given time. But it wasn't directly linked to the PyroSim or FTS output data. So what we've done is we've added this Friedolf correlation in, and it requires the use of a previously run FDS model that includes plot 3D output that includes the visibility based on SIT. And then what Pathfinder can do is, as occupants move through the geometry, it can query the plot 3D output, determine the visibility at that location, and then appropriately adjust their speed based on that visibility data. I don't have an exciting model of that, but I have a validation model here that I can show. It's a simple setup with a series of 7 rooms here with various visibilities ranging from as low as a ½ meter up to fully clear visibility. And the expected velocities are shown down here on the movement speed chart. And we can see over here on the right, I've actually reduced the opacity of the smoke as displayed by the post-processor just to make it easier to see that you see the occupant on the left moving quite slowly and the occupant on the right room is unencumbered. That wraps up all of the movement research that I have time to cover in this presentation. I'd like to thank the entire team at Thunderhead Engineering for all of the work that went into this research. We have a really talented group that has made all of this work possible. Thank you for your time, and I look forward to answering any questions that you may have.
Okay, great. So we'll just wait a moment for Brian to make his way over here. It's about the time it'll take everybody else to come over. Hey, look at that. So quick.
Good morning, Brian.
Good morning.
Can you hear me all right?
Yeah, hear you just fine. People.
All right, I see a couple. We're only going to have a few minutes here. We can try to keep the schedule on track. I see from Jason, generally poor adherence. Yeah, I mean, we're not trying to model how people are actually going to social distance themselves. Basically, you can just tell people to do that in the model or not. I do expect that it probably would not be maintained and that it'd be abandoned. It obviously depends where you are. Where we are in the middle of the country, people are a lot less adherent to that. But our goal in Pathfinder was to make it so you could describe a certain scenario and then use the quantitative outputs of it to at least then quantify what went on, right? What was the exposure or how far apart were people? What's the next one, Brian?
So just impressed on how much development we did on the social distance feature in such a short time. Have you thought of inserting a probabilistic factor representing the likelihood of compliance to social distance, which can possibly change it?
Kind of like the first one. Yeah, that's probably a good way to handle it, is just kind of let somebody put in some kind of range or normal distribution. That's a good suggestion. I don't think that's on our short term, but that would probably be.
We'll make a note of that. Yeah.
Right now it's kind of handled by profile, so we'd have to allow it to vary on an individual level to support that.
Yep. And just a heads up, Steve, I'll let you in when it's your turn. All right. So anyway,
maybe one more and I'll have to go start up the next talk so we don't get too far behind schedule.
Yeah, last one. What are the main differences between Pathfinder and I think maybe EVAC, but he has HVAC. I think EVAC, probably FDS plus EVAC.
FDS EVAC. If we say it's FDS EVAC, I mean, it kind of comes down to the calculation models under the hood. FDS EVAC based is on a flow field kind of model of how the people move. So it's sort of like particles in a fluid, whereas Pathfinder is an agent-based model where each individual occupant sort of modeled more like, agents in a video game.
I will say we have one more question that was on the stage. I'm just bringing it in, which is for egress within smoke visibility from FDS, what sampling rate would be needed for the plot 3D data? I'm worried it might generate quite a lot of data for complex buildings.
It does and it can.
I mean, I've always recommended that you set the frame rate so that you can capture any important transients in the data. So you would want the band narrow enough to capture any.
Right. It could be 30 seconds or 20 seconds, but it wouldn't necessarily need to be many times a second. And also that's kind of just our initial pass on that one. I think we'd like to change it to use something more like a slice at eye height or something. Still, it's quite a bit of data, but we either got to get the data or not. So.
Well, that's great. Well, thanks, Brian, for the talk and for Q&A.
All right, you can kick me out of here and I'll run over and start up the next talk.
All right, we'll see you in a bit. I'm just answering a couple things. Actually, I can answer here. So Pathfinder is agent-based like FDS plus EVAC, but where it uses a flow field and I would say social forces, Pathfinder uses a little bit different model for moving people through the domain. So there's a Pathfinder technical reference that I'd recommend looking at for how we do our cost functions and moving for movement decisions.